So I won't be talking about black holes nor cosmology, at least directly. I'll be talking about cosmic rays and those measured by the Pierre Observatory, and not any kind of cosmic rays. I'm going to be talking about the highest energy particles that we know in nature. We have known about the existence of these particles for several decades now, but they're pretty rare. So at the highest energies, we have like 1 particle per square kilometer per century. So if you want to detect more than 1 particle per century in your square kilometer array, you need to build a big experiment. Fortunately, when these particles arrive to the Earth, they interact with the atmosphere and they produce this huge cascade of particles that can reach the ground, and these extend for several kilometers. So if you detect these showers, we can reconstruct the shower and get information about the primary particle. Now, and this is what the Pierre Auger has done. This is the biggest observatory dedicated to ultra high energy cosmic rays in the world. It has an extension of an area of 3,000 square kilometers. It's located in Argentina here, and this is the layout of the experiment. I'll go in detail on this later. This is a big collaboration with around 400 scientists from 70 countries. And we are building the array and the whole experiment since at least 2 decades. So the data taking started in 2004, we're in 2023, and we are planning to extend the life of the experiment until at least until 2035. Now the experiment, so in this area, each point that you see is a water tank, and we detect the charged particles that arrive at the ground with the Cherenkov lights that they produce when they cross the water, and we have here some PMTs. And during the night, we can see the fluorescent lights that the shower creates when it's traveling throughout the atmosphere. So this fluorescent light is basically the excitation or the de-excitation of the nitrogen molecules as the electrons progress through the atmosphere. And let me just show you a couple of pictures. So you can see this is very flat, and here you can see the tank separated by 1.5 kilometers, and you can count if you have good eye, like 7 or so tanks. And this is a close-up of one of the tanks, and you can see here at the top you have the fluorescence detector building with 6 telescopes. Each door here is hosts a telescope, and this is just a LiDAR unit to monitor the atmosphere. Now, over the years, we understood that we wanted to target the highest energies, but we understood that it was interesting to go a little bit lower in energy, and we have built several extensions, several detectors to probe the lower energies. In particular, we have now a denser array, actually 2 dense arrays, one of 433 meters grid and another one of 750 meters. We have installed scintillators buried. This is good if you want to detect directly the muons of the shower. You see that this is important. And we have an engineering array, radio array. We are exploring this technique, and it's showing to be very promising in the future. Plus, we wanted to continue to see showers through the fluorescence technique. So we have created some telescopes that can be elevated, and we call those it, and we have 3 telescopes here at this place in Coelho. So all in all, this is what the experiment currently can cover, from something from 5 times 10 to the 16 to the highest energies, to the highest energy. And the way that we detect these showers can be in one of 2 ways, the main techniques. So in one case, we can, in very dark nights, so no moon, no windy, no big clouds, we can look at the development of the shower. So you can see here the profile recorded. And the good thing about this technique, even though it's has a duty cycle of only 15%, the good thing is that the integral of this curve is directly the energy of the shower. apart from some small corrections. So it's a colorimetric measurement, like it is done in the big accelerated experiments, particle physics experiments. One thing that I want to point is the maximum of this profile, and I'll be designating this as Xmax, and I will discuss more about this later. Just remember, whenever I say Xmax, I'm talking about this maximum. The other way is just sampling the shower at the ground. You can get the direction by the arrival time of the stations to the stations. And if you look at the lateral distribution and you pick a reference distance, the signal that you get here will be your energy estimator. Of course, this one is very good for statistics because it runs all the time. The problem is that it's very Monte Carlo based. So this is an estimator that you need to really calibrate. And we do this when we have events that can be simultaneously detected by the fluorescence detector and the surface detector. And this is one of the biggest strengths of the array. And you can see here the different calibrations that we've done for the different kind of arrays and the detectors that we have. And also this is very good to test things about the shower, as you will see later. Okay, so this is a very fast introduction because I don't want to focus on the techniques. I want to focus on the results. I want to tell you what we have learned so far during these past nearly 20 years. So the first thing is that this is the ultra energy cosmic ray energy spectrum and is far from featureless. So you can see several bumps here. And the good thing about these bumps is that it means that something has happened, either in the source or in the propagation, but something has happened. So it's good to have bumps. We now have a structure, a newly discovered structure called second knee. So we have the knee here around 10 to the 15, but there's another knee in this region. There's what we call an ankle, which is believed to be the transition between galactic cosmic rays to astrogalactic cosmic rays. There's the famous suppression. This suppression is very important. So this means that the cosmic ray energy spectrum doesn't extend to infinity. So there's something happening that creates an horizon. Now, let me just say that this horizon can either be explained by a propagation effect, like the GCK, so the interaction of the cosmic rays with the cosmic microwave background, or simply there's no more energy in the sources. And recently we have claimed to see another structure, which we don't know what it means currently, called the instep, which is this instep. We had made up a name at some point. We had a huge discussion in the collaboration for this. Okay, so we have the spectrum, and we can also look at the arrival direction. So one of the things that we did was to look at the large scale, so to a dipole, so to speak, to see whether there was some preference from cosmic rays coming from the galaxy, which is nearby, or if cosmic rays, this kind of cosmic rays, are from extragalactic origin. As you can see in this map in galactic coordinates, this is at the center of the galaxy, and you can see that the dipole is very much deviated, and this proves with a very nearly 7 sigma effect. This proves that there's no accelerator in our galaxy strong enough to produce these particles. People have proposed this for several years, but now we have a proof that this is true. We have also tried to identify sources that if these were protons and at the very high energies, the magnetic fields, the extragalactic and the galactic magnetic fields is not enough to bend enough these particles, and there could be some degree of pointing. But unfortunately, what we saw is that there's an excess around the Centaurus region, but this excess is only a 4 sigma effect if you try to compare with what you expect from isotropy. And we have compared to several catalogs, and the most promising is the so-called starburst galaxies catalog, but again, this is not a discovery, it's just 3.8 sigma, so we are accumulating statistics to see whether this is true or not. Then another thing that I think that is very important that this observatory can do is to look for neutral particles. So if I can find a photon or a neutrino, this will pinpoint to the source directly. But more important, most of these theories on dark matters, super heavy dark matter, or these exotic beam models that try to explain the origin of these particles always predict these neutral particles. And it's very easy for us in Auger to look for photons and neutrinos. So for photons, we just look to showers that are muon depleted, that have a little muon content at the ground. For neutrinos, we look at showers that are very inclined. So normal showers cannot travel through the atmosphere while neutrinos can, or that they came from below the Earth. We have not seen this, but we continue to look because at some point, if we have protons traveling, we were expecting, or if there are particles around some mass around these accelerators, we would expect that these neutrinos and photons will be there. So, and we are getting close to these propagation effects. These are the shades here. Now, we have also analyzed the composition. So we're tracking for the composition. And for that, our most sensitive quantity is this X max. Okay. So because if you look here, these shower profiles, I have here for proton and iron, we expect the composition to be something between proton and iron, can be helium, can be carbon, but that it has to be something between these. But if you look at these, you see that proton showers are typically more deep, while iron have the X max more shallow, and also proton fluctuate more than iron showers. So we can use the templates from simulation to try to infer the composition, and this is what has been done for different hadronic interaction models. And what you can see in this plot as a function of the energy is that at low energies, we seem to be dominated by protons, and then protons gradually disappear, and then this becomes helium. You can see there's a peak here, and then again this disappears, and then we have nitrogen, and there seems that we don't have any kind of iron. So the composition seems to be changing. And if we could believe in this, in fact, there's much more things that we could do, and this all is new in Auger. So we could try to look at the arrival directions, taking the composition into consideration. And when we do this exercise, we see there's a suggestion of around 4 sigma that the cosmic rays coming from the galaxy are heavier than the ones coming from outside the galaxy. This is very interesting. And if you try to fit everything, the X max and the spectrum, you have these nice features. So you're dominated by proton at low energies, then you pass to helium, then you pass to nitrogen. Finally, you get some iron. And these would be saying that the source, the astrophysical source mechanism is accelerating these particles to a power of the mass of the particles. And this will be very interesting. Of course, that now we need to believe that the models are doing the right thing, okay? But, and this is a big but, we have also checked the sanity of these simulations and we have done those looking at muons. So if you look at the shower, you see this is a shower development. The shower, whenever you have a pi 0, it goes into what we call the electromagnetic sector. So it decays into photons, and then it builds an electromagnetic shower. But when you have mesons, they might decay and produce muons, and these muons will propagate towards the Earth. So if I count the muons, I'm looking at the hadronic interactions that are occurring at the top of the atmosphere. And we have done that using inclined showers. You can see here that if I have an inclined shower, the electromagnetic particles will die out very rapidly, and only the muons will be able to get to the ground. So when I look at this footprint and I look to the normalization of the footprint, I'm basically counting muons, which are proportional to the energy. So no deal, I cannot do anything because muons and energy is convoluted. But for these 281 events, they aren't, because they were measured simultaneously by the SD, the surface detector, and the fluorescence detector. So I can get the energy from the fluorescence detector, and the surface detector will tell me the number of muons. And when we've done this exercise, we reach this plot here, and you can see these lines are proton, this is iron. You can see that the data seems to be slightly above. We have done the same thing with the buried scintillators that we call omega at lower energies. So this is these two areas here. And this seems to be all iron or slightly above. But now if you plug the information of the X max that was measured by the FD, what you see is that there's no model that can explain what we are measuring in Auger. So basically, these are all the compositions, and models are struggling. These are post-LHC models, and there's no model that can explain simultaneously the number of muons and the X max in Auger, neither at low energies nor at high energies. This is what is usually called the muon puzzle. Okay? Now, we've done more in recent years, and we have also measured with great effort the relative fluctuations. And what we saw was very striking, because now for the fluctuations of the number of muons that you get to the ground, we have very large error bars, of course, because we have few data right now. But this is between proton and iron, and more, the shaded region is the composition when one interprets it with the FD, using the X max. So this is very striking. And if you use this paper here, which actually motivated this measurement, these might be signaling that that what's happening, what we are missing is not at the highest energies of the electronic interactions. There's something at the lower energies that we missed, and it's a cumulative effect that is building up this muon puzzle, this muon axis, apparent muon axis. And this is very strange, because accelerator should have covered this region, but it seems to be this that the data is telling us, and we will keep investigating. Now, there's many other measurements that we've done over the years. So we measured the cross section, again, very high energy, and it's in accordance with what we expected. We've measured the average longitudinal profile shape, and again, is what we expected. But whenever you look to things that are related with muons, we get answers that says to us that our showers are very badly described. So what can we do for the future? Okay, so for the future, it's no secret. So the collaboration is undergoing a massive upgrade. We called it Auger Prime. So the main idea is to put a scintillator on top of the tank. And with this scintillator on top of the tank, scintillators are mostly sensitive to the electromagnetic particles. They count particles, and the electromagnetic particles are more numerous, while the tank is both sensitive to the electromagnetic particles and to the muons. So if you combine both, you can get a measurement of the electromagnetic and the muonic component at the ground separately. We are also taking advantage of the radio antenna, because when you incline the shower, because this scintillator is a plane, it becomes very inefficient. But with radio, we can continue to look to the electromagnetic component of the shower. And we are also installing these underground muon detectors, and we have upgraded our electronics. So all in all, we've been doing this for some years now, and this is the status of the array. As you can see, red means that everything is set, and you can see that we are about to finish it. Until the end of this year, everything will be done. Now, why is this so exciting, and why are we extending the experiment until 2035? Because now we can do something that we could not do previously. Now we can have these multi-hybrid events. So here you have an event. This is a real event measured with this array, where you can get the information from the scintillator in red, from the Water-Cherenkov detector in blue, from the underground muon in black, and even the radio. So you're looking into the shower with different detectors, and you can ask different questions. So there's a high number of things that you can do. And whenever we use just the FD and the SD, we discovered that we got the shower completely wrong. So now it's going to be much more potent. So this is my last slide. So I just want you to show the plethora of measurements that we will have in Auger. So we have the radio measurements, we have the hits, we have the Amiga detector, which are the the buried scintillators. We have R&D projects like Marta, where we're using RPCs, resistive plate chambers, putting them below the tank to check to detect the muons directly. We have the infill, we have the Auger prime, the scintillator, which we call SSD. And for me, particularly, the interesting thing is that if there's something wrong with the electronic interactions, we are in the good spot, because the energies that we have at the LHC currently, if you take the proton and you take a nitrogen target, the equivalent energy that you get at the center of mass is about 10 to the 17th, where we have this bunch of detectors. So if there's something wrong, we will definitely pinpoint what's wrong there. So this is my summary slide. So we are having an increasing coherent picture that is emerging from Auger phase 1. If we believe the models again, it would be great. We would understand everything. Let me just point that even though I presented that there seems to be a natural evolution, this natural evolution requires that very hard injection spectra. This means that these machines, these astrophysical machines that produce these particles, would have to be highly efficient, more efficient than anything that we have ever seen. So before we say that we have these machines in the universe, we need to be sure that we understand our data. For that, we need to know the mass composition. To know the mass composition, we need to really understand the electronic interaction models, and this will be done by Auger phase 2. And that's all. Thank you.